Okay, so how do we do this? Well, there's a couple ways you could do it. You take the negative and change all the signs in here and remove the parentheses, which is, I think, the way the book discusses it. But really, we can handle this just like we do with any other number. When we add or subtract, we must have the same name, which means we have to line up the place values. So I put the x squareds under the x squareds, and the x's under the x's, and the ones or whole numbers under the ones. And we are now subtracting down these columns. So we have 9 minus a negative 13. 9 minus negative 13, which becomes 9 plus 13, which is 22. Negative 7 minus 2 becomes negative 7 plus a negative 2, which is a negative 9. So negative 9x. And 3 minus 7, negative 4x squared. Does that all look familiar? I don't. Friday feels like it was a long time ago. So when we add or subtract, we must have the same name. And then we just keep the same name. We add, we subtracted down the columns. The x squared stayed x squared. The x's stayed x's, and the ones stayed ones. When we multiply or divide, we don't. Not only do we not have to have the same name, but we also combine the names. And when we add, 7x squared and 3x cannot be combined. They're separate digits. They have different place values. So 7x squared plus 3x is just 7x squared plus 3x. But when we multiply 7x squared times 3x, we can combine that. Multiply the count. 7 times 3 is 21. And then we also multiply the names. X squared times x is x to the third. So the first thing we're going to explore today is dealing with the powers on that variable. If I have x to the fourth times x to the third. Now, some of you might know that that has to become what? X to the seventh. Because x to the fourth is 4x's multiplied together. X to the third is 3x's multiplied together. Well, if we multiply them with each other, now we have a total of 7x's multiplied together. When we are multiplying variables with exponents, we are multiplying, but the appearance is we're adding the powers. 4 plus 3 is 7. So y to the 9th times y to the 5th becomes y to the 14th. X to the 8th times z to the 3rd becomes, trick question, x to the 8th times z to the 3rd. Why can't I add the powers? Because the base is different. This number here that's underneath the power is considered the base. They have to have the same base, x and x, or y and y. I can't combine x and z. Those are different names. I can multiply them and get x to the 8th, z to the 3rd, but I can't combine their powers. So what if I have something like x to the 5th, y to the 3rd times x to the 3rd, y to the 4th? Well, I can combine each name separately. What's x to the 5th times x to the 3rd? X to the 8th. Y to the 3rd times y to the 4th? Y to the 7th. And I can even throw numbers in there. 8x to the 7th y, z cubed, times negative 5, x squared, y to the 3rd, z squared. I combine the counts. 8 times negative 5. A lot of people screw up and just want to say, oh, 8 and negative 5 make 3. Remember, we're still multiplying, so the counts still get multiplied. So 8 times negative 5 is negative 40. But then we're going to take each variable on its own. X to the 7th times x squared is x to the 9th. Y times y to the 3rd, y to the 4th. We think of this, even though we don't write it, we think of it as y to the 1. It's 1 plus 3 is 4. Z to the 3rd times z squared, z to the 5th. Very good. What's that going to give us? Some of us know that is x to the third. Remember, x to the fifth is 5x's multiplied together, divided by x squared is 2x's multiplied together. Now we can cancel out. Remember, we can reduce fractions by dividing out top and bottom by the same thing. We can divide out an x. We can divide out another x. And now we just have 3x's, or x to the third, over 1, or just x to the third. So when we are dividing variables with powers, with exponents, we're just subtracting the powers. 5 minus 2 makes 3. So if I have y to the 13th divided by y to the 7th, I get y to the 6th. If I have z to the 9th divided by z to the 4th, I get z to the 5. Or if I have p to the 38th divided by m to the 21st, I get just that. Very good, because they're different variables. How about p to the 38th divided by p to the 27th? Perfect. P to the 11th. X to the 4th to the third power. Of course, x to the 4th is 4x's. To the third power means 3 times. Now how many x's do I have multiplied together? 12 of them. That's x to the 12th. When we have a power, a variable with a power to another power, the appearance is we're multiplying the powers. 4 times 3 makes 12. So if I have y to the 8th to the power of 5, I'm going to get y to the 40th. Or z to the 5th to the power of 4, z to the 20th. Good. So we can work with our variables and their powers and combine them and have all sorts of fun with them. So we've seen things like this already. Where we combine. What do we do again? 5 times 9, combining the counts, is 45. X to the 8th. What we're really doing there is combining a single-digit number with another single-digit number, multiplying. So what happens if we have one of those numbers is not just a single digit? What if it's more than one digit? What if we have something like 7x squared times 5x minus 2? This is exactly like having 4 times 32. If I were going to do this long multiplication, I would put the number with the most digits on top, the 32, multiplied by 4. And then it's going to be 4 times 2 is 8, 4 times 3 is 12. Over here, I can do the exact same thing. 5x minus 2 times 7x squared. And do 7x times, that's not 2 though, that's negative 2 is going to be a negative 14x squared. 7x squared times 5x, 35. 7 times 5 is 35. X squared times x is x to the third, or x cubed. Just like multiplying whole numbers. Now remember, we said we can have 2 digits in a place value here because there is no carrying in algebraic numbers. At 13, we can't carry the 1 over. So when we do this multiplication, we can end up with big numbers like the 35 and the negative 14. The fact that it's more than 1 digit doesn't matter. It can stay in that place value. So here we're going to have the 3x squared minus 9x plus 13 times 5x to the 4th. Again, I don't have to line up that x to the 4th under anything in particular, because when I multiply, we don't need the same names. So now we have 5x to the 4th times 13 is 65x to the 4th. Now it's positive, so I'm going to put a plus in front of it. I have to have a symbol that links it to the next term or next digit. 5x to the fourth times negative 9x is perfect. Negative 45, and that is x to the fifth. And then 5x to the fourth times 3x squared. Perfect. 5 times 3 is 15. X to the fourth times x squared gives x to the sixth. 2 plus 4 is 6. And that be our answer. So I want you guys to try one. Try that one in your notes quick. See what you come up with. So, walk me through it. Well, let's do the 7x squared plus 12x minus 15. 3x third. So technically, if we're doing it this way, the first thing we would do is 3x to the third times negative 15 is negative 45x to the third. Good. And then, perfect. 3x to the third times 12x is a positive 36x to the fourth. And, perfect. 3x to the third times 7x squared is 21x to the fifth. How many of you got that? Now, you started out telling me do 3 times 7. A lot of you, if you had high school algebra and still remember it, were taught to do something called distributing. Where instead of writing out, this is actually the full way to multiply. This is the long way of doing it. This is real multiplication. But most of what we were taught was shortcuts without the real method. So I wanted to show you this just so you see that it can be multiplied out just like any other number. Now the shortcut we've been taught. Now this shortcut would work with whole numbers as well. It's just we carry with whole numbers, so it doesn't work so well. But I'm going to show you. It's called distributing. To distribute, and that's a U, not an O. To distribute, we just leave it as it is sitting here, and we start with 3x to the third times 7x squared, which is 21x to the fifth. 3x to the third times 12x, which is a positive 36x to the fourth. 3x to the third times negative 15 is a negative 45x to the third. It's just a way of saving some steps and shortening it up, taking up less paper. Now, believe it or not, I mentioned it, so I'm going to show you how. Don't write this down because I'm never going to make you do it this way with whole numbers. But let's say I have something like 453 times 2. If I don't, well, 2 isn't going to work. Let's do times 4. It'll work better. We're used to doing it out this way. 4 times 3 is 12, carry the 1. 4 times 5 is 20, 21, carry the 2. 4 times 4 is 16, plus 2 is 18, carry the 1, like that. We could do that with distributing. Where it is 4 times 4 is 16. 4 times 5 is 20, drop the 2. 4 times 3 is 12, so 2, drop the 1. Just the carrying is a little clumsy. Distributing doesn't really shorten this problem for us any. Up here, however, because when we do algebraic numbers we don't carry, distributing does shorten that process a little bit for us. So, I mean, everything we do with algebraic numbers and variables is something we do with regular numbers, too. It's the same processes, the same concepts, all the same rules apply. It's just it looks different because there's variables in there. So,
I understand the 36. How did you get to the fourth?
The x to the fourth?
Yeah.
Because we had x to the third times x. That's x to the 1, so 3 plus 1 is 4. So now what if we have 2-digit numbers like this? Well, just like when we had, 24 times 73. We had to do the 3 times 4 and then the 3 times 2 like that. And then 7 times 4 and 7 times 2. And if you remember, even in the first week, we wrote that out as 2 tens plus 4 ones and 7 tens plus 3 ones and multiplied them out. Well, the reason I did that is because now when we look at numbers like this, it follows the exact same process. This is 2x minus 7 and 5x plus 4. And we are multiplying. So now we've got 4 times negative 7 is negative 28. 4 times x squared, 8x. We're done with the 4, we move over to the 5x. 5x times negative 7, negative 35x. Now we've always been taught to either put a 0 or leave a blank space here. Negative 35x has to go under the other x's, like that anyway. 28. Then 5x times 2x is 10x squared. And now we combine. Negative 28 doesn't have anything to combine with. 8x and negative 35x is a negative 27x. I'll leave it up to you to confirm that 8 plus negative 35 is negative 27 on your own if you want to. And 10x squared is just 10x squared. That's it. So I can have 7x plus 3 times 3x minus 5. And the exact same process is going to apply. Where am I going to start? Negative 5 times 3 is negative 15. Negative 5 times 7x, negative 35x. Then what? 3x times 3 is 9x. So it's a positive 9x. Has to go under the other x here. Then 3x times 7x, 21x squared. So now we're going to combine. Of course, the negative 15 has nothing. Negative 35 and positive 9. Negative 26. And then 21x squared. Now, some of you, again, if you're remembering your high school algebra, we're taught a process called FOIL, right? FOIL, again, is a shortcut. What I showed you down here is the long way, the full way to multiply out 2-digit algebraic numbers. FOIL is just an acronym for a shortcut. F stands for first. You multiply the first 2 digits. 7x and 3x make 21x squared. O stands for outside. So the outside 2 digits, 7x and negative 5 make negative 35x. I stands for inside. So 3 and 3x make positive 9x. And L stands for last. 3 times negative 5 is a negative 15. And of course here you can combine the negative 35 and the 9x. So we've got 21x squared. Negative 35 and 9 make negative 26x. And then negative 15. We get the same answer. And the FOIL is shorter. But again, I don't like shortcuts because shortcuts only apply in specific circumstances. For example, oops, anybody still writing that down? You need a second? Okay. Like I said, I don't like shortcuts because the first step in using a shortcut is knowing when you can use the shortcut. And shortcuts, most shortcuts only apply in a specific set of circumstances. For example, if I give you this problem, FOIL don't work anymore because now we got this middle digit here. So it'd have to become FOIMAMOIL. Not so pleasant anymore. But if we just do the long multiplication, 2x squared minus 7x plus 11, and 8x minus 3, and we're multiplying. it's still going to work. Negative 3 times 11, negative 33. Negative 3 times negative 7x is positive 21x. Negative 3 times 2x squared, negative 6x squared. Now again, we'll usually leave the blank spot here. 8x times 11, positive 88x. Make sure that's under the other x. 8x times negative 7x, negative 56x squared. And 8x times 2x squared, 16x to the third. Very good. Then we've got negative 33. 21 and 81 makes a positive 109x. Negative 6 and negative 56 is a negative 62x squared, and 16x to the third. What do you think? I'm thinking it's time for you to try one. Try that one in your notes. Let's see how you come out. Okay, so what'd you get for an answer here? 6x to the third plus... No, I'm getting a positive 23. And a negative 20. Because you got 35x and negative 12x makes the positive 20. All right, no problem. So there we go. Next step, dividing. 42x to the 8th divided by 7x to the 5th. Just like multiplying, we combine the counts. What is 42 divided by 7? 6. And then we also combine the names. X to the 8th divided by x to the 5th is x to the 3rd. And it is that simple. So here, what are we going to get? 27 divided by 9 is 3. X to the 3rd, because 5 minus 2 is 3, and y squared. We think of this as 1. 3 minus 1 is 2. Well, that's not tough at all. So let's do a multiple digit number divided by a single digit number. Now I'm going to show you something here that you may not have ever seen before. 486 divided by 2. 2 goes into 4 twice, there's no remainder. 2 goes into 8 4 times, no remainder. 2 goes into 6 3 times, no remainder. If there's no remainders, I can just take each digit here and divide it by the 2. And it works out perfectly. Same thing happens in algebraic numbers. X to the 4th divided by 18x is 36 divided by 18 is 2. X to the 4th divided by x is x to the 3rd. Negative 54x to the 3rd divided by 18x. Well, negative 54 divided by 18, negative 3. X to the 3rd divided by x, x squared. 72x squared divided by 18x. 72 divided by 18 is 4. It's a positive 4, so plus 4. X squared divided by x is just x. There it is. Not really, no. So like here, usually I start at the front and go to the left. Division, we usually go left to right, just because that's how we're used to doing division. So 35, x to the 7th, y to the 3rd, divided by 5, x squared, y squared. 7. Yep. Just y, yep. 35 divided by 5 is 7. X to the 7th divided by x squared, we subtract powers. 7 minus 2 is 5. Y to the 3rd divided by y squared, well, 3 minus 2 is 1, so it's just y. 25x to the 5th, y to the 4th divided by 5, x squared, y squared. Positive 5, x to the 3rd, y to the 2nd. 25 divided by 5 is 5. X to the 5th divided by x squared. 5 minus 2 is 3. Y to the 4th divided by y squared. 4 minus 2 is 2. Now negative 40x to the 3rd, y to the 5th divided by 5. X squared, y squared. Negative 8. X. 3 minus 2 is 1, so just x. Y to the 3rd. 5 minus 2 is 3. Very good. I think we've got it. How's about this one? We're taking this to a power, so we're going to do the number first. What is 2 to the power of 5? 2 to the power of 5 is 32, right? 2 times 2 times 2 times 2 times 2 is 32. Now, x to the 7th to the 5th power is x to the 35th. We are multiplying those powers. So what if we have 5x squared y to the 5th to the power of 6? Is that going to be 30? Say no. No, the number still gets raised to the power. That is 5 to the 6th power, which is 5 times 5 times 5 times 5 times 5 times 5. Or 5 to the 6th power on your calculator, which is 15,625. Then what? X squared to the power of 6. Now we multiply the powers. 2 times 6 is 12. Remember, when you add a variable with a power to another power, you're multiplying the exponents, multiplying the powers. And then y to the 5th to the 6th power is y to the 30th. So you've got to be able to switch back and forth between working with numbers where you actually take the 5 to the power of 6, then working with the powers on the variables where it's just power times power. So it's a little bit tricky there. So in the big book, there'd be some examples. On page 339, exercise 13-4 has some of these. And on page 342 through 343, exercise 13-5 has some other examples of this that you should maybe do. Are you writing that down? I'll pass some old quizzes and stuff back to you. You have test 2 or 4 or somewhere? Don't know why that one hits you so hard.
Is it just me?
It did. It was just you, but it's pretty much.
This one, yeah,
Yep.
this one. I came up with the same answer.
Alright.
Here, let me see if I got my answer. Answer is right.
Okay.
I must just have looked at the wrong spot or something. So you've done all your other corrections?
I think that's
Okay. So I'll run those through for you.